Any question before we start? We will start at 11, okay? You ready? Let's start. Last time we talked about Dr. Hubbard model, okay? And you are about to get homework today about this. Homework today is the same as this, okay? To do the same thing that I did, but by yourself. It's not quite the same when you do it by yourself, believe me. But this is kind of the answer, okay? I show all the calculation here. It should not take too long. The part that could take a while is that, okay? You will be asked to use RK4, not RK45. Okay? Try to see if you get the same thing I got or something else. Alright? Is that easy enough? So this will help you to review the material and try to do what Douglas and Hubbard did. Okay? They did without a computer like you. So your answer should be more accurate. Agree? Douglas Hubbard is what, 19 something? 75? Or 76? Long time ago, right? So your answer should be better. Alright? We talk about Taitel-Barnea. Okay? We start with mass balance equation for the gas phase, for the liquid phase. From Taitel-Barnea, I told you that you look at it by yourself, right? But basically, they have equation for X, mass balance equation. They combine them together, they can get equation in terms of VSL something. Okay? Did you take a look at that? Or you don't take a look until you have a quiz or something? Will you? Would you like to? The quiz has to be more difficult than that, I think. But okay, take a look at that. It's just arithmetic. Substitute in everything and we get equation 3.124. Alright? Just relation for X and W. Then we also talk about this equation, right? They do the math, they show, okay, mixture velocity has a relationship with O up, liquid velocity and gas velocity inside the liquid slab like this, okay? So last time we ended here, alright? This equation is about combine those mass balance in terms of VSL, okay, and adjust it a little bit. So you may see that there are some assumption, okay, adjust it a little bit, or actually there's no assumption. This in terms of this, rearrange it, we get this equation, HLSU. Good. And that HLSU tell us that we may not know the field profile. Okay. We may know just, okay, HLS, liquid volume fraction in slug body. Okay. And we know velocity of gas inside the slug. We know the void fraction in the slug. We know VSG, VTB, then we can directly calculate HLSU. So this means we can calculate HLSU even before we solve ODE, right? Got it? This is very important, especially for the case where hydrostatic head. dominate the system. Is the majority of the pressure drop come from hydrostatic head? Okay, this matter. Alright? Any question before we move on for this lecture? No? Today we are going to talk about Taitel-Barnea. Taitel-Barnea is a better method compared to double Hubbard. It's also a long time ago, but people still use it. Currently, in petroleum industry, they actually use something that is like worse than that. Okay, you heard about like some correlation-based model. Correlation-based model. What I'm talking about? Correlation-based model. For example, Beck and Brill, McCarthy, Douglas, Eden. What is this? McCarthy, Brill, and something. Okay, there are several methods. Eaton, those things. That's a correlation-based model. They still use that. Not even mechanistic. Okay. So what we have here is better. In Olga, which is kind of industry standard for multiphase flow calculation, especially for subsea pipeline, it's not like this one. Okay. The reason is that in Olga, it is about transient simulation, but this one is steady state. Okay. And this steady state condition is as correct as it can be. Okay. So compare this to Olga, maybe we compare some like different thing, but okay. At steady state, this is good. Okay, good enough. Even people use a simplified form, not the full form. Okay. Don't restart my computer yet. Okay. Why do we use simplified form? What do you think? So let's think about this. Yeah, we want to do something quick, right? If you have a film profile, is that kind of film profile going to be the same all the way, every location in the pipe? Probably not, right? When there's a change in angle, everything has to be recalculated. Okay? When there's a change of VSL, VSG, can it be the change of VSL, VSG in subsea pipeline? Isn't it like mass flow rate of liquid and mass flow rate of gas is constant? There's a phase change. There's a phase change. When pressure drop, gas come out of solution, right? Okay. So there's a phase change. Temperature also change if it is subsea pipeline. Temperature change, pressure change, so that's phase change. VSL, VSG will change, right? This is phase change. So every time that VSL, VSG change or angle change, fluid property change, you have to do film profile again. Okay. How many slots in there, or how many sections that we want to do everything? Maybe it's a little bit too much, okay? And it can just do steady state. Okay. So it is accurate, but maybe a little bit too much. All right, but it's perfectly fine for the case of laboratory thing, because the pipe is short. At most it's like 50 feet or something. It's not 100 miles or 50 miles. I don't know if we have 100 miles, but we for sure have 50 miles subsea pipeline. Okay, maybe in North Sea. Alright, that's the application of it. We have double Hubbard. A better model, Taitel-Barnea. In Taitel-Barnea, I already show you the assumption. They don't assume gas velocity equal to liquid velocity inside the slug. No, they don't assume that. Okay? And they show that, okay, slug liquid slug unit liquid hold-up can be calculated directly. Okay? Even though we don't know the film profile. That's something that we should know about. So Taitel-Barnea introduced the momentum balance. We don't prove, we just take the equation. Okay? The left hand side is the change of momentum, kind of momentum rate with respect to z, and this is the kind of the change of momentum of force with respect to z, and other term is other force. So it's kind of force balance. Summation of F equal to ma, and the left hand side is the ma term, ma, and other term. Look at this one. Tau f. Where's tau f? Tau f, it will be what? The flow is in that direction, right? Film move forward. So friction is in that direction. What about tau I? Okay, gas move forward faster than liquid. That's the assumption. So this is the balance in liquid phase. So liquid will see that the interface drag it forward, right? Okay. So when liquid see that gas drag it forward, why tau I is negative? Let's stop for a moment and check stratified equation. Stratified equation, you remember stratified equation? This one. Stratified equation for the liquid phase. We have minus L dpdL. Let's zoom in a little bit. Minus L dpdL. And we have tau I. Tau I is positive. Look at that. Tau I is positive. Rho g sin theta is negative. Okay, memorize this. Tau I is positive. Tau W is negative. Gravity term is negative. Let's go back to the slide. You have your book too, right? So in here, instead of positive tau I in the liquid phase, I have negative tau I. Okay, gravity term, previously I have it as negative value, now I have it positive. Pressure term, I have kind of the same, minus dpdz. This is also minus dpdz. Okay, and I have one more term extra. Tau f is like tau wall. Back in stratified flow is negative, this time is positive. Okay. This has to do with the coordinate system. Okay. We say z is that direction. Whatever flow or move in z direction is positive. So gravity sin theta term is in z direction, so it's positive. Tau I is forward, so it's opposite to z direction, so it's negative. Tau f is dragged it back, right? So it's positive. What about pressure? What is that about for pressure? Anyone want to tell me why we have that?
Which one?
The pressure term. You just come back, come on. We have that pressure term. Okay, that pressure term, it is the pressure drop across delta z. Okay, so pressure on this side is we call P. Pressure on another side, what do you call? What do you call this pressure? So it's P plus dP dz multiplied by delta z. right? So this thing is what? That direction. So it's negative. This thing is this direction. So it's positive. So minus P, so I get minus P minus dP dz delta z and minus this pressure. Okay. This has to be plus because this P is in the positive direction. So that cancel with that is the same as the governing equation. Okay. Alright, it's not like always just flip the sign. No, we have to look at the coordinate system and do it again term by term. What about the new one? We have the new one. Rho G cosine theta. You like that? Where does that come from? We have never seen that before, right? What we are doing here is what? Force balance or momentum balance in the stratified region. Okay, it is a stratified region. Look at the control volume. That's the control volume. That's the stratified region. Where does that term come from? Who read the book before come to class? Give me the answer. Yes, did you read the book before the class? No. Did you do homework?
Yeah.
Oh, you did. Okay. Who read the book before come to class?
I didn't reach to that part.
You didn't reach that part. Okay, skip. Victor, you reach this part?
Yeah, it's just another thing. Okay.
What Professor Shoham told you?
What?
Professor Shoham is the one who wrote the book, right? You talked to him by reading the book. What did he say?
It's due to the profile of
The difference in height. There's a change of the height. Okay. What is cosine theta? Cosine theta is what? G cosine theta is perpendicular to the flow direction. But right now we are doing the force balance in the flow direction. How come cosine theta appear over there? Anything wrong with that? Nothing wrong with that. It's like rho g h. Pressure equal to rho g h. Hydrostatic head. That term is to account for the difference in the hydrostatic head. Hydrostatic head is rho g h. Okay. Every term is divided by dz, so that is kind of h, rho g and h. Negative sign come from what? Negative sign means liquid move in the direction that minimize the center of mass. Okay. Look at this part. Oh, dHf by dz, is that positive or negative?
It's positive, but because it's going in the
Oh, no. Doesn't seem like you did today homework yet. dHf by dz, where does that come from? Previously we solved ODE, double Hubbard equation, right? We get dHf by dz. Is that positive or negative?
That figure is negative.
Okay, because when z go up, h go down. So that term has to be negative, right? So minus 1 multiplied by minus 1. So totally, this whole term is positive, right? Correct? Positive means force is in what direction? That direction. Positive means the force is in the z direction, which is opposite to the flow. Force should be opposite to the flow. Of course, look at this height. This height is more, this height is less. I don't know how, we don't focus on how we have that yet, but now let's take a look at the sign. The sign is correct. The sign tells us that, hey, when we have liquid height increase in the flow direction, the hydrostatic head kind of push backward because on the right side is more than left side. So now the sign is clear enough, is it? The left side is like MA. Okay. Alright. So we have one for film, one for gas. Okay. And can you check if this equation is the same as what in your book? These two equations. Where does that equation come from? You have the book, do you bring the book? Which page?
101.
What?
101.
101. Are they the same?
Yes, sir. Yeah, they are the same.
Look, exactly the same. So I take the equation from the book, and the equation from the book is also the same as in the publication, okay? Without any derivation, I just explain you about the sign. I will show you how do we solve it, okay? First, let's take a look on how we solve it, not whether it's correct or not yet, okay? That's that model that they propose. I put it here. Minus rho g cosine theta dHdz greater than 0 falls due to the difference in the gas pocket height is also in the positive direction. Okay. Is it okay? And the explanation I put here is that gas phase tends to slide over the liquid phase and lower its center of mass. So the movement of gas phase is not really because of gas is heavy, right? And due to hydrostatic head, it pushed backward. No, it's not about that. It's not like, hey, gas on this side has a lot of height, gas on this side has less height, so more height has more pressure. No, the movement of the gas phase is about the movement of the liquid phase. Okay, so I put note over there that when we have liquid, like they try to adjust the level to be uniform, right? That impact gas too. Okay, and gas when it slide over, so think about something like that. So if you have a mass, the battery is at an angle, it slide down. Okay, that's kind of the idea. So this is how we have negative sign over there too. Because it slides down, so it kind of moves to the plus z direction. Alright? No further explanation given in this course. We focus on how we solve it. The next step, like we look into detail, that will be directly from the publication. Okay? Alright. In the publication, you can find how they give you each term. Okay? And they explain it term by term. At least the sign, you should know about the sign. Okay? For example, I give you this equation in the form of something like that, and ask you to circle the right sign. Would you be able to do it? Yes, of course. You are very smart. Okay. All right. Very good. So at least you should know something about the sign, because that ensure that you understand the concept. Okay. How do we get each term? Each term is the same as stratified flow. Nothing special yet. Okay. Tau F, VLTB, absolute, multiplied by VLTB. And as we discussed in stratified flow, we put absolute value over there so that if film fall backward, the sign will change automatically. In today's homework that you're about to get, this thing, angle is 0, right? Angle is 0, so maybe it's easy. There's nothing flow backward because angle is 0. So when angle is not 0, there's a chance that it can flow back. Okay, so if you use rho v square, you're not going to get the right answer. You have to use rho v multiplied by absolute value of v, like that. And when we calculate force, we use the real velocity, not the relative velocity. Okay, tau g is the same. Tau I is the difference. The velocity is the difference between gas phase and liquid phase. It's the shear stress at the interface. F sub I, where does that come from? Closure relationship, right? That comes from closure relationship. F sub F, everything here is fanning friction factor, okay? Unless I do something wrong. So F sub F comes from Laplace type equation. D sub F, D sub G, D sub F doesn't have plus SI. Did we talk about that ever? In stratified flow? Yes. So for the film, it sees that the point that have velocity equal to 0 is not included in the interface, but gas flows so fast so that at the interface it's like a lot slower than the gas phase, and it say like, okay, maybe it's kind of stationary, we have I over there. The rest is the same, Fi depending on the stratified smooth or stratified wavy. If you have rolling wave, it will be more. Okay, the equation for rolling wave is given in your book, not here. Here's the governing equation. What is the term that we normally try to eliminate when we do combined momentum equation? Pressure. Okay. We top one minus bottom one. The pressure term is gone. Good. That's combined momentum equation. Okay. We do some math and we get that. That is similar to Douglas-Hubbard got. Yeah, but it's longer. The equation is longer. You have equilibrium height by assuming that the top part numerator equal to 0, so for height. You have critical level where the slope equal to infinity by assuming that the bottom part equal to 0. The way to solve it is the same as one in Douglas-Hubbard, but it is valid for inclined case. Okay, let's go back a little bit on how do they solve it. We have expression for relative velocity Vf and relative velocity Vg. Okay, those are not actual velocity, relative velocity. So this part comes from, what is that? Relationship for pickup rate, right? Mass pickup rate is delta V multiplied by rho up equal to delta V multiplied by rho up in the film and in the slug body. Same thing is true for the case of gas. Good? So that's nothing new yet. Okay, how about this question? Which part in the film that VLTB is highest? Oh yeah, question.
We were saying that the pickup was only for liquid phase, right? But why we have in this case like a pickup relationship for gas too?
Gas in front of the slug body, is that moving faster or slower than the interface?
The slug body?
Interface have gas in front of it, right? That interface, does it move faster than gas? Yes, if it moves slower, it cannot trap gas inside. So it's eating gas or trap gas inside, right?
Okay.
So
one equation is for the tail of the slope.
one is for...
One equation is for the...
No. It's not about one for the tail, one for the front. Those two, typically, it comes from the front. Okay? Look at one of these. HLTB, if you do the front of the slug is the tail of the fin, right? You may add E over there. HLTB E, which is at the end, multiplied by VTB minus VLTB E. If you put E, you have to put E over there too. Okay. So it's a relative velocity multiplied by hold up slightly in front of the slug body. That is almost X. If you multiply by density, you get mass pickup rate. Right now it's kind of volume pickup rate. Okay. And this part, you get this equation when your point of interest is in the slug body. This equation is where your reference line is in the film. This equation comes from when your reference line is in the slug body, and both come from moving coordinate system. You remember that lecture?
Yeah.
For gas, it's the same. Okay. In the moving coordinate system, right, moving observer will see the gas mass move across a boundary with this volume. That volume. So it's a relative velocity multiplied by cross-section area for the line inside the slug body. And that must be the same volume that comes from the film part. Okay, we have the film part, right? So the film part and the slug part. Actually, those two lines should be almost at the same point, but it's just different phase. Okay. So in the film part, what is the relative velocity the moving observer see? VTB minus VGTB, right? VGTB is the gas ahead of it. What about relative velocity inside the slug body? VTB minus VS or VGLS. Okay. Relative velocity multiplied by hold up, or in this case it's void fraction, equal to relative velocity multiplied by void fraction. Otherwise, the amount of pickup and the amount that go inside is not the same, and we have expansion of the slug length. We don't want that for steady state or fully developed. I'm sorry, for fully developed. Question? It's okay now. What I worry is this equation correct, or I copy it correctly from the book, or is there a typo? Is it? It's correct already? 3.138.
Yeah, page number 102.
It's the same? Yeah, okay. So from the governing equation, we eliminate pressure term. Then we have kind of X equation, but of course we miss rho and we miss AP here, right? Kind of X equation, XL, XG, not exact, but kind of, okay? Then we take the derivative. See this one? I take the derivative of VF with respect to Z. How do I do that? VTB, is that a function of Z? No. VRS? No. HRS? No. Only HRTB is a function of Z. So that's the rest I can take it out from the derivative. Rearrange it, take the actual derivative, I get that. Okay. Why do I need dVF by dZ? Because the MA part, when you look at the MA part, that VF is relative velocity. It's not actual VLTB. No. That is VTB minus VRS. Right? And the equation that we try to rearrange it, which one? The combined momentum equation, that one has this term and that term. We cannot solve it. We have to rearrange it in terms of the height by dz, like before. Okay, we have combined momentum equation. I take the derivative with respect to the v sub g, or relative velocity or relative gas velocity. then I get that. Okay, substitute it into the combined equation, into that equation. 3.136. Just substitute it in, I get a long equation, that one. Alright? Look at this one. dHR by dZ, dHR by dZ. Oh, dHF by dZ. HF, HL. Is that the same? Is it? It's the same thing. I just use where's HF come from? Actually, maybe I cosine theta. Or this come from this part, right? In the governing equation, that HF is a film height. Film height and liquid height will be the same thing in film zone. So combine those three together, rearrange it. I do it step by step for you, but maybe it's look a little bit messy. Then we get a governing equation to be solved with RKF45. You can use Euler method, doesn't matter. And you will use Runge-Kutta method tonight or this week. Alright? For this new homework. Question so far? If you don't have question, I have question for you. You know that, right? No question? Isaac. To solve this equation, we need initial point. How do we get it? What is that? What is the value that we use?
What is the value?
What do you use?
You assume HF is equals to H as when Z is equal to 0.
Oh, very good. Okay. So we get height as z equals to 0 to start the equation, right? And that height comes from hole up. If you have time, like you do it at home, like in the homework, use goal stick so that you convert hole up to height through geometric relationship. If you do the test, just assume it's the same. Okay? So we can start the equation. When do we stop? When do we stop? Option 1, okay, option 1, LS is known. When LS is known, we don't know the film length. So we stop whenever mass is conserved. Okay? So we keep doing the integration, but we stop whenever the mass conserved. Option 2, frequency is known. When frequency is known, we don't know the slug length. So we assume a slug length, like the one that you're going to do for the homework. We assume the slug length. When we assume the slug length, we know the slug unit length, then we know the film length. We stop when we need to stop. Then we check if our initial guess of slug length correct or not. Guess it couple times, do linear interpolation, get the right slug length. I hope tonight homework will be clarify this point. If it's not clear enough, you just get, if you do just half, you get half. Okay, try to do everything. It's not that difficult because the solution is in here. You can compare against me, not your friend. Okay. Alright, basically you can solve this. Okay. What about HLLS? Hold up, liquid hold up in the slug body. Yes, where do we get that from? HLLS. We need HLLS to know HF at z equal to 0, correct? Where does that HLLS come from? Do you happen to have a friend named Gomez or last name Gomez? That come from them, Gomez and all 2000. Yeah. Close relationship. What about VTB? Do we need VTB? Do we need it? Where do we need VTB? Where is that going to be? VTB has anything to do with this?
In the equations.
Yeah, in the equation.
This is the equation.
Which term has VTB? You see this VF? Has VTB, right? That is VTB, and that is VTB. Where does VTB come from? What? Victor.
We use the C0.
Closure relationship. C0 is 1.2. V drift is from who? Nicklin something? Benjamin? Whatever closure relationship, you get that from, right? Do you understand what I'm talking about? Yes? Huh? Do this. Okay. Alright, you can solve it. I shouldn't have you solve it tonight too, right? It's just a little bit longer. See what I'm saying? Every term is a function of height. Is that true? VTB is known, VLLS is VM, or otherwise we calculate VJLS from the closure relationship. The horizontal flow is a VM, right? Alpha LS. Oh, what's this? Is that a typo? Alpha TB squared. I don't think we have something like that. What's in your book? HLTB squared. Okay, I'm sorry, it's not.
No, but it's
Oh.
correct.
It's correct?
Yeah. 1 minus HLTB.
Okay, 1 minus HLTB squared. Oh, okay. So that's 1 minus HLTB squared. Everything can be solved, it's just a little bit longer. And that's nothing special. I didn't hide you anything. So to be fair, I did what? 2 lines, the blue line, and I did both, right? Double Hubbard and Taitel-Barnea. You should do both. Okay? Do you think you can do both? Yeah. It's just a little bit more term, use the same method. Okay? So if you can do just one of them, how long does it take to do any of this? 6 hours? If it takes 6 hours, I'm fine. If it takes more than 6 hours, it's too much. Homework is too much. Alright? Yes, what do you say? One or both? Do you want it to be fair or you want it to be easy? Let's have it as usual, as future student and past student. How about that?